All right, Organic Chemistry 1, we're going to start off by looking at some free radical chemistry this morning. And the first question is, which of these four radicals is the least stable? And I asked this question to my students who are online already, and they all got it pretty quickly. I see they all had the correct answer, and they all chose this one. Why? Because it's vinylic. Right? A vinylic radical is going to be really, really, really unstable. Now, out of all these, the one that's going to be the most stable would be this one here because it's resonance stabilized. The other two, A and D, are not resonance stabilized. But again, we're never going to see a vinylic radical in organic chemistry because they are so unstable. So it's something that all students should be able to recognize. It's like a vinylic carbocation. You're never going to see that either. All right, let's move on to question 4. And this one involves, the mechanism of treating an alkene. This is just cyclohexene. It's a molecule we see all the time in Organic Chemistry 1. We're treating it with HBr and peroxides. And remember, peroxides just means an organic peroxide, which is a radical initiator, right? So HBr and peroxides, and then we add HBr across the double bond. Now, of course, you all recognize these conditions, right? These are anti-Markovnikov conditions, aren't they? Anti-Markovnikov addition of HBr. But in this case, you have a symmetrical alkene, so there's no Markovnikov or anti-Markovnikov addition to worry about. But that's not what the question is. The question is only asking us which one of these would be an intermediate in the reaction, right? Which one of these would be an intermediate? And in order for you to figure that out, in my opinion, you need to know a little bit about the mechanism of free radical addition. Okay, you need to know a little bit about the mechanism of free radical addition, right? Because you start off with your organic peroxide, right? And that is going to undergo a homolytic bond cleavage like this to produce a couple of radicals, right? So you end up with a radical like that, and this is, again, initiation. And then that radical is going to react with your HBr. Okay, we're going to react with that HBr, and we're going to end up with an alcohol, and we're also going to produce a bromine radical. So we end up with a bromine radical plus an alcohol. But then what happens once we form that bromine radical, right? The bromine radical is going to add to the alkene. That's the first step of the propagation, right? Okay, we're going to have our alkene. Oops, let me get my black pencil out here. There we go. The bromine radical, where is it, is going to add to that double bond, right? And we explained that this step is why we get anti-Markovnikov addition, which again is neither here nor there, but we end up with this intermediate where the bromine has added to the ring, and we're going to end up with a radical like this. So the answer is A. That is going to be the intermediate, right? Because the bromine adds first. Remember, when we do the Markovnikov addition of HBr across the double bond, the first step is the proton transfer to produce the most stable carbocation. But when we're doing radical addition, the first step is the addition of the radical to produce the most stable radical. And now, again, here we have a symmetrical molecule, so there's no Markovnikov or anti-Markovnikov to be concerned with. Now, ones that you could eliminate right off the bat are going to be the carbocation and this anion over here. We're not going to have either of those. But again, you need to recognize that the first step of addition of bromine to this is going to be to the double bond, right, like this, to produce this intermediate right here. There we go. Well, let's move on and let's talk a little bit more about radical stability. And this is question number 5. I'll zoom in on the question first, and then we'll look at the possible answers. But you have this interesting molecule. You have an aromatic ring. Excuse me. You have a propyl group on this side, right? Then you have a methyl group down here. All you're doing is taking this molecule, and treating it with bromine and light. So you know that these are free radical conditions, right? Radical generating conditions. You take bromine, you shine a light on it, and you end up producing bromine radicals. So you would end up making a bromine radical. The first step is going to be a hydrogen abstraction. The next step is a halogen abstraction. But anyhow, it's just asking us, what would you expect? And we have 4 answers here. If you look at A, you have the bromine replacing one of the hydrogens from the methyl. In B, you have the bromine tacked onto the end of the propyl. In C, you have the bromine attached to the methylene that is attached directly to the aromatic ring. okay, from the propyl group. And then in D, it's just kind of in the middle, right? It's in the middle of the propyl. Could anybody suggest which one of these would be the best answer for the bromination of that compound? I'll zoom out a little bit here. It's kind of hard to squeeze the whole thing in the screen. But anyhow, could anybody make a suggestion out of which one of these, excuse me, would be the expected product? Yeah, I agree. Yeah, one of my students is saying it's going to be C. Now, could we get more products than just C? I think so. Yeah, but I think that C would be the main product. Now, why would that be? Because the first step, like I said, once you produce the bromine radical, the first step in the propagation is going to be the hydrogen abstraction. So if we draw the molecule out, okay, so if we draw the molecule, and I'm going to draw it and highlight this hydrogen here, so H2, CH3. Okay, so the first step is going to be bromine is going to abstract that hydrogen like this, okay? And then we're going to produce a radical. And that radical is going to be this. So we're going to have the radical in the benzylic position. And remember how I told you that benzylic radicals are highly stabilized. Now, if you're saying, well, hold on, Mr. Dion, there's a benzylic position here too. That's true. That is true. That would make a stable radical. And that's why I think you'd end up with some of A as well. However, the position where I have the radical drawn right here, this is the more stable radical because not only is it benzylic, but it also has this ethyl, if you will, attached to it, or this carbon group here attached to it, which donates some electron density to it and serves to stabilize that radical. So it's not only benzylic, it's benzylic in secondary. Whereas if you form the radical down here, it would be benzylic in primary. So that would give you the most stable radical, and therefore that's where the bromination is going to occur, the halogen abstraction. And if you want to get down with it and really just draw the whole dang mechanism, you draw the bromine and you could draw the halogen abstraction, so which is going to look like this, and that would give you product C. So it's just a matter of, you know, we spent a lot of time talking about carbocation stability, and good news is that carbocation stability and radical stability are very closely not analogous, but are not related. I'd say they're more analogous. You know, a tertiary is going to be more stable than a secondary, so on and so forth. So benzylic is going to be stabilized not only by the resonance through the aromatic ring, but also by the carbons that are attached to it. All right, let's move on to question number 6. This is one that I would expect my students to do pretty well on. I think my students are pretty confident in this question, but let's take a look at it. Come on, you. There we go. It says, which reaction, and there's 4 different reactions for you to look at, gives an efficient synthesis of this molecule. So this is 1-bromo, 2-methylpropane. I'll just give you a second. I want to see if my students can come up with an answer. And don't be shy. Could anybody suggest which one of these conditions would be the best? So if we were to do A, so A is just a free radical bromination, right? And remember, that's going to be regioselective for the most substituted carbon. So in this case, you'd end up with this molecule, or you end up with this, and you'd end up with the bromine here. So that's not going to be it, okay? In the second one, you're just taking a primary alcohol and treating it with HBr, right? The first step is you're going to convert this into a good leaving group, and then the bromide is going to come in as a nucleophile, and you're going to end up with this compound where you just substitute the bromine. But as my students are saying, it's C, right? Because it's an anti-Markovnikov addition of HBr, right? This carbon is the one that's richer in hydrogen. So if that one takes the bromine, that's an anti-Markovnikov addition. I like that. So here we go. Now, if you're saying, well, Mr. Dion, you get the same product here, but it's asking you which one is going to give you the most efficient synthesis. right? We know that this is going to be highly selective, whereas if we treat this with HBr, okay, the primary alcohol, not only are we going to end up getting this product, but we're also going to end up producing some of the carbocation and getting elimination as well. So we would end up with that compound, plus we'd end up with isobutylene as well. All right, so you end up with a mixture in this case, whereas in this case you only end up with one compound. And the last one is just a bromination, where you're going to add a bromine to both of the carbons in the double bond. So we could draw that out. It's going to look like this, where you got a bromine here, and a methyl group like that. So again, the most efficient synthesis would be the anti-Markovnikov addition, because B will give you a mixture of products, and that's not very useful, is it? All right, let's move on to number 10. Another one I think my students would be confident in. This one right here, just a quick one. It says, at which of the indicated positions would a bromine radical react at the fastest rate? Who could tell me where a bromine would react the fastest? Go with your gut. Yeah, I think my students are definitely on the right track. Absolutely. Okay. The students are all saying the same thing. They're all saying, Mr. Dion, I think it's B, right? Why is it B? Because this is a benzylic position. So benzylic. So that's going to produce the most stable radical. Why is it so stable, right? It's because of resonance stabilization, right? If you draw the radical out, okay, you'd end up with the radical here. And we looked at something that was pretty close to this radical earlier on. And you should be able to draw all of the contributing resonance structures. So you should be able to do that and keep pushing that unpaired electron around the ring. All right, so benzylic position. So number 2 is where the bromine's going to react at the fastest rate. And let's try one that involves this reaction. So number 12. You know what? Number 12, we didn't talk about polymers, did we? So, I would never, this question is not going to be on your final exam. I don't know why I threw it in here. Anyhow, I just thought it might have been an interesting problem. But anyhow, I will not ask this question, okay? Because this is about a polymer. And polymers they come up in a bunch of different places in the textbook. If you read all the practically speakings and medically speakings, and I hope you do, they're really interesting. But you'll notice that our textbook brings up polymers probably 10 times throughout the book. So, and then there's a chapter at the very end of Organic Chemistry 2. It's the last chapter you do that covers polymers. But again, I'm not going to ask you this question, and I don't know why I threw it in here, but it is kind of interesting. You take an alkene like this, and this is a radical initiator here, and you could make a polymer that would look like this. But again, I'm not going to ask that, so we'll scratch that one off. We'll say, don't worry about polymers, because it's not going to come up. All right, let's turn our attention to oxidation and reduction. Really important chemistry. And you know what? In Organic Chemistry 1, we don't deal with nearly as much oxidation and reduction as you do in Organic Chemistry 2, but we do talk about it a bit. Okay, and one of the reactions that we talked about in detail was ozonolysis. It says here, ozonolysis of which terpene? And a terpene is just a naturally occurring compound. I mean, there are tens of thousands of terpenes. They all have the same formula where I think it's C5H8 or something like that, and then some kind of multiple of 5. So you can see that all of these compounds, they all have 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, they all have 10 carbons. So these would all be terpenes. A diterpene would have 20 carbons. A sesquiterpene has 15, so on and so forth. But anyhow, if you were to treat all 4 of these compounds with ozonolysis conditions, this is a good question. Can anybody tell me which one of these would produce these 3 compounds? So all it means is you take them, since they're alkenes, right, and you would treat them in step 1 with ozone, and in step 2 you would treat it with DMS or zinc and water. Could anybody tell me which one of these would produce these 3 interesting compounds? All right, I'm getting some answers already. I dig it. And actually, this is very fast. So I'm very impressed by my students who are able to answer this really quickly. Yeah. I think I agree with you. I think I agree with the people who are saying A. Now, one thing that I picked out right away, and again, you might solve this a little bit differently than I do, but you could basically do the skill builder, right? Where you cleave all the double bonds and then you could just draw what's left over in each case. You could do that. But something I noticed about A and B, okay, the reason that it can't be C and D is because in order to make this molecule, which is acetone, nail polish remover, you'd have to break here or here, right? Because when you break those two red squiggle lines that I have, you would end up producing acetone. Let me make them a little bit neater. Whereas in the molecules at C and D, there's nowhere that you would produce those, right? Now, the problem with B is that if you end up cleaving this double bond right here, you can see that the carbon on the top, that would end up producing formaldehyde, right? That would produce the simplest possible aldehyde, and that's not one of the compounds. So the answer must be A, right? And again, if I just use green, I'll use a green pen here. If you break this bond or cleave that bond and cleave this bond, you can clearly see that you would end up with acetone from down here. Here you would end up with this aldehyde, like this, which is this compound here. And then you would end up with everything else, you'd end up with this carbon, double bond, and you end up with this compound right here. And so the answer is A. So a little practice on ozonolysis, which is an oxidation reaction. Let's try question number 6. Question number 6, what is it? It says reduction of a triple bond. So this is alkyne chemistry. This would be covered in what, chapter 9? The reduction of a triple bond to an E or trans double bond can be accomplished with which set of the reagents? I'll just throw that out there to my students. Yep, absolutely. Alkyne to a transalkene. I knew you would all get this question correct. Yep, absolutely. You're all 100% correct that it's sodium metal and liquid ammonia, right? And the reason why is because it proceeds through a radical anion. If you want to review that, but you end up proceeding through the radical anion, it's where you have a radical on one carbon and then you have an anion on the other. And because of electron-electron repulsion, they try to get as far away from each other as possible, and that's why you end up with trans, reduction to the trans. Anyhow, there you go. Let's move on. What was the next one I had? It was question number 13. So let me move down to question 13. And again, you can see a lot of these questions don't involve things that we learn in Organic Chemistry 1. Here we go. Excuse me. It says, which set of reagents could be used to affect this conversion? So we're taking trans 2-butene and we're making this diol. I have a question for you guys. Does this look like syn addition of the 2 hydroxyls or anti-addition of the 2 hydroxyls? And it's not a trick. I'm not trying to fool you. And the book isn't trying to, the question isn't trying to throw you for a loop. Does this look like syn or anti-addition to you? Absolutely. This is syn addition, isn't it? Syn addition. So we're adding syn addition of 2 hydroxyls. Absolutely. Absolutely. So could anybody tell me what the best conditions would be? Which ones would be the best conditions for syn addition? Remember, we learned many different conditions for syn addition. So A would be anti-Markovnikov addition of water across a double bond, right? This is one is borane, or borane and THF, and then hydrogen peroxide and sodium hydroxide. So this is anti-Markovnikov addition of H2O. So we're not adding water here. The next one is proiodic acid. That would do a cleavage. Again, this isn't covered in our textbook, so don't ever worry about that being the answer to anything on your exam. But basically what that would do is that would cleave it so that you'd end up with two molecules of this. But again, don't stress about that reaction. So you'd end up with that. Okay. The answer is C, isn't it? Right. This is one of the conditions that we actually learned that is in our textbook, is that for syn dihydroxylation, you can use potassium permanganate and sodium hydroxide. Remember, I told you that this was really strong conditions, very forcing conditions. Okay. But it does work to do a syn dihydroxylation. And D, that's not going to do anything. So we'll just cross D off the list like that. All right, there you go. Syn addition. Let's see. So the whole proiodic acid, this is just a cleavage of vicinal 1,2-diols. But again, it's not covered in our textbook, so don't worry about that as being the answer to anything. I wouldn't do that. Oh, by the way, surprise, no, that's not. All right, let's turn our attention to spectroscopy. And remember that during the final exam, you're not going to have, a table of IR shifts. You're not going to have a table of proton shifts. You're not going to have a table of carbon shifts. But I don't think you are going to need it to solve any problems that I would ask you about spectroscopy. Now, what's the first question I had here on the list? Was number 1. Okay, it says number 1, which ketone? So we have a ketone here, 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 a bunch of beautiful ketones. Which ketone will show a carbonyl absorption with the lowest frequency? So the lowest frequency. So could anybody tell me which one would absorb at the lowest frequency? So remember that the frequency of absorption, so frequency, and you don't have to memorize this formula. It's going to be 1 over 2 pi times the square root of the K divided by the mu, right? So this is the mu is the reduced mass. But since we're dealing with a carbonyl, the atoms in the bond are the same every single time, right? It's just a carbon and an oxygen, so that's neither here nor there. It has to do with K, right? K is the bond strength. So since K, the bond strength, is in the numerator, the weaker that it is, the lower the frequency of absorption is going to be, right? If this is low, this is going to be down low, right? Because you see that wave number is directly proportional to, it's the square root of the K, but either way, it's directly proportional to K. So the lower the bond strength, right, the lower the wave number. And this is one of the concepts that we went over in the IR chapter, is that when you have a conjugated system like this, the carbonyl is going to be weakened. Why? Because of resonance, right? If we zoom in on that molecule, right, we can draw a resonance structure where it's going to look something like this, okay? And since that carbonyl has partial single bond character, which the other ones don't, so you have the oxygen up here and you have a carbocation right here. So since that carbon-oxygen bond has part single bond character, right, that you can clearly see in this resonance structure, which doesn't exist for any of the other molecules, it is a weaker bond. So again, it's the conjugation that renders that bond weaker, and therefore it's going to absorb at a lower frequency. All right. And again, it's something that we covered in the slides if you don't remember, but that's definitely an important concept. The weaker the bond, right, it's going to have a lower frequency of absorption, right? If you think about what are the things, and this is a question that I always used to ask on quizzes when I taught organic chemistry for chemistry majors at UCCS. I'd always ask them, what are the factors that affect wave number? Right, and there's 3 things. One is the bond strength. The other one is the reduced mass. And there's one more thing, or sorry, this doesn't affect the frequency, I shouldn't say, but affects the signal. And that would be the polarity, right? Because we talked about how the more polar a bond is, the better antenna it acts as to absorb the infrared radiation. Anyhow, let's move on from there. Let's try number 2. It says, which compound is consistent with this infrared spectrum? I'll try to zoom in on the infrared spectrum here for a second. And again, something I like to do sometimes is just take the old ruler out here, and I find this can be really handy. But, you know, as organic chemists, we like to draw a line maybe around, you know, 3,000, and let's draw another one, I don't know, around 1,700 maybe. Okay, and we'll see. If I zoom out here, now that you've had a chance to look at it, could anybody suggest which one of these compounds would be represented by this infrared spectrum? Yeah, I agree with you all. Yeah, I see that my students are getting this one pretty quick, right? Because you obviously have an oxygen-hydrogen stretch here, and I agree with you that this looks to me like it's an alcohol, right? I think an alcohol is probably the second easiest functional group to recognize in the IR. I think a carboxylic acid, which is in this problem over here, is even easier, but anyhow, that's neither here nor there. But you can see that here we have a ketone. Okay, so that's not it, and especially we don't have any carbonyl. So we'll put here no carbonyl. So here we have an aldehyde. I got ketones on the brain. So here we have an aldehyde. It's definitely not an aldehyde because again, and here we have an ester, and it's definitely not an ester because we don't have a carbonyl. It is the alcohol. Alcohol. All right, and there we go. Definitely an alcohol. Let's try question number 3. Question number 3. Uh-oh. You can see some of Mr. Dion's scratching on here. But anyhow, let's give it a try. It says, which is the most reasonable structure for this IR spectrum? And I realize that this might not be the easiest IR spectrum to read. Let me try to zoom in on it here. Let's do the whole ruler thing. And we'll draw a line at around 1,700. So this is 1,700 here. And we'll draw a line around 3,000. And that might help a little bit. I know it's a little grainy, but you can still pick out the low-hanging fruit, right? I would say the most important, signals are here. There's obviously a carbonyl in the compound, okay? And then we also have a signal right here. You don't see a lot of signals around, you don't see that every day in organic chemistry, and it's a little grainy, but it goes 2000, 21, 22. So this is around 2,200 reciprocal centimeters. Does anybody remember what would come out around 2,200 reciprocal centimeters? Not 2,250, but 2,200. And I don't think there's a nitrile in any of these answers anyway. So the one at 2,200 must be a carbon-carbon triple bond, right? So we have an alkyne in the molecule. We also have a carbonyl in the molecule. You can clearly see that there's no OH stretch, so it's definitely not an alcohol. Another thing I noticed is that we don't have an aldehyde, right? If you look at 2750, right, in 2850, there's no aldehyde here. So we can cross the aldehyde off. Where's the aldehyde? It also doesn't have a double bond in it. So then we're down to C and A, right? Because they both have a triple bond. Could anybody tell me why or how I can determine that it's A, the ester, and it's not C? Okay, so the answer is A, but can anybody give me another explanation as to why it's A and not C? What am I missing from C that's not in this spectrum? There's something really important. Yeah, the CO stretch, I agree with you, Allison. Yeah, you're both 100% correct. Okay, one person says the carbon-oxygen stretch, and I say hot diggity damn, you're 100% correct, right? Because this is a mega carbon-oxygen stretch, which is indicative of an ester. Okay, so that means it's an ester. And then somebody else said, well, look, Mr. Dion, here you've got a terminal alkyne. You should see a sharp signal at around 3,300 reciprocal centimeters. And you go up here and it's a ghost town, right? There's nothing up there. So that is double proof that it is the ester A and that it is not C, the ketone. There you go. Hey, that's great work, you guys. Excellent. Excellent work. All right. Let's see here. Number 4. Didn't I already mention this one? I'll just throw this out there to my students. Try to zoom in on it the best I can. It says, which structure is consistent with this infrared spectrum? This is one I would expect everybody to get know 100% and not spend a lot of time on it. Yep, absolutely. I knew it. You know, I know you guys could probably solve this faster than me. That's right. You see this big old oxygen hydrogen stretch, but this is from a carboxylic acid, right? It's oxygen hydrogen stretch from a carboxylic acid. There's only one carboxylic acid in here, so it's definitely B. You see the nice, beautiful carbonyl over here. Maybe this is a carbon oxygen stretch down here, but either way, you can definitely tell that's a carboxylic acid, isn't it? Right? Let's try question number 11, which I think is a good one. Question number 11, where is it? Yeah, question number 11. We looked at a bunch of problems like this when we were practicing Proton Nmr and when we were practicing carbon-13. I think this is the first thing we did, is say, how many signals would you see for this compound? So when we're talking about carbon NMR spectra, how many total signals would you see? All right. Hot diggity darn. Good grief. You guys are all 100% correct. Okay, and I don't think this is an easy question. You know, I don't think it's an easy question, right? But you know that if we draw a bond line structure, which might help a little bit, we just draw a bond line structure, okay, of this compound like this and this, right? I think that why students get this right is that you know there's free rotation around this carbon-carbon bond, right? So you know that these three carbons all give you the same signal, don't they? Whereas this is the only quaternary carbon in the whole molecule. This is the only methylene in the whole molecule that's sp3 hybridized, right? We have another CH2 over here, but I mean, that's vinylic protons. We have another methyl group over here, which has no relation to any other methyl group in here. And then we have this sp2 hybridized carbon over here. So that's a total of 1, 2, 3, 4, 5, 6 signals. We get a total of 6 signals here. And again, the reason why these ones that I'm putting the yellow highlighter on, the reason why those 3 carbons, all 3 of these are equivalent is because there is free rotation around this bond. So we would end up with a total of 6 signals in this case. All right. Give me a thumbs up if that makes sense. If it doesn't, feel free to, shoot me a question about it. All right, cool. Well, so that's, I think it's a really good question about carbon, and we spent quite a bit of time, looking at structures and saying, well, how many signals would you get for that? How many signals would you get for that? Next one I had was question number 12. Oh boy, this is an interesting one. Okay, so I apologize that it's not the easiest for me to zoom in on this one here. So I'm just gonna, let's look at the answers first. The question is just asking, here's an NMR spectrum. Which one of these compounds is it? Let's look at the compounds quickly first. We have 4 aromatic compounds. Here we have an aldehyde. Here we have an ester. Here we have an ether. Here we have an amine and another aldehyde. Here we have a ketone. Okay, whatever. All right. Well, those are the compounds. Let's go up and look at the NMR, okay, and see what we can figure out from the NMR, okay? Could anybody tell me, where this signal would come from? It's something that we discussed, We have a shift that's around 10 parts per million, at 10 parts per million. So this is around 10 ppm. Could anybody tell me what kind of proton that would come from? When you have a proton signal at around 10 parts per million, and it's not trying to fool you, exactly, it's an aldehyde, right? So aldehyde. I want to go back and look at the compounds. So A is an aldehyde. We can cross B off the list. C is an aldehyde, and D is not an aldehyde. So there we go. So now hey, that's pretty good. We narrowed it down to A or C. It's one of those two. Let's figure out, and what's the difference here? They both have ethyl groups on them. So you see that A, look, has two ethyl groups that are chemically equivalent by symmetry, and C has two ethyl groups that are chemically equivalent by symmetry. And that makes sense because we see that we get a quartet and a triplet, right? We have a quartet and a triplet. And for C, we would end up with a quartet and a triplet, right? That's indicative of an ethyl group. So really, we can't use the ethyl group to differentiate between A and C. The only other thing we have is this here. Okay, what I have in the green box. Could anybody use that to differentiate between A and C? I'll tell you the answer is yes, you can. But does anybody remember what it means when I have a doublet of doublets that are kind of symmetrical like this, that are both kind of pointing towards each other? I did mention it in class this semester. And if any of you are taking the lab with Mr. Geiger, he might have talked about it too. I'm not sure. Okay, so when we have a doublet of doublets in the aromatic region, right? These are the aromatic protons. Okay, but whenever they're like this, you have a doublet and then you have another doublet and they're kind of pointing towards each other. And this is a pretty crummy sketch that I'm making here. What that means is that you have an aromatic ring that has 1,4 substitution. So you've got one group here and you have the other group over here like this. Okay, that's called para substitution. So para substitution. If you look at A, it's mono-substituted, right? There's only one substituent on the aromatic ring, all of this. But if you look at C, it's para-substituted, right? You have one group on this side and the other group over here, right? Sometimes, again, we call it 1, 2, 3, 4. We'll call it 1,4 substitution. So the answer is going to be C. All right. So again, it's a para substitution is something I did go over with you one time in the class, but it's important, and make sure you know that. It would really be the only way you could differentiate between these two. It would be tough to use chemical shifts in order to do that. All right, so para substitution, you see those two doublet of doublets that kind of point in towards each other. All right, that's question number 12. I had a couple more picked out here. Let me see. Where are they? Question number 13. Let's take a look at 13. Oh boy. Here we go. And you know that this here, right, this signal here, that's a zoom in of this thing here, which represents one proton, right? So this is one proton. I don't know if you can see that. I hope you can, but this says 6 protons, this says 2 protons, and this says 1 proton. Do you remember when we looked at Proton Nmr? You remember that before we got into elucidating structures, we spent some time talking about alkyl groups that you would see every once in a while in a spectrum. For example, we talked about when you see a triplet that integrates for, when you see a triplet that integrates for 3 protons and a quartet that integrates for 2 protons, that means you've got an ethyl group. Does anybody remember this? No. Does anybody remember this? When you have a septet that integrates for 1 proton and a doublet that integrates for 6 protons. So this is a doublet and this here is a septet. Does anybody remember what kind? Yes, 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 yes. Absolutely. It's an isopropyl, isn't it? Right, so this is an isopropyl group. Yes, 100%. Right, and you can see that A has a tert-butyl group, so that's not it. In B, we just have a big old butyl group here, so that can't be it. In C, we have an isopropyl group, don't we? Kind of, okay? We have this over here, which would count like an isopropyl group, but in D, there's no isopropyl group in there either, right? You just have this, you know, this would actually be a sec-butyl group, right? This would be sec-butyl alcohol. And so the answer is most likely C, and I definitely think it is, you know, that's the right answer. But if we just draw a bond line structure of it out here kind of quickly, okay, right, does it make sense? Do the other signals make sense, right? Because here you'd have the doublet for these guys, right? This is the doublet that integrates for 6 protons, this one here. Then you have the septet, right? Which is going to be this proton here, so septet for this guy here. Now, this proton here, I mean, that's only going to integrate for 2 protons, isn't it? That's going to give you a doublet, right? That's going to give you this doublet over here because it's only going to be split by this proton. And then the hydroxyls usually don't split. They're usually just, you know, a singlet. And so we would get a singlet for this guy over here. So yeah, I think that C is definitely consistent with the structure of this compound. And this would be isobutyl alcohol. All right, so isobutyl alcohol. Okay, let's take a look at question 17. Question 17. All right. Ooh, these ones are more challenging, where we have not only a proton, but a carbon-13 NMR spectrum. So something that I talked to you about very briefly, and I've made a point to mention it to you, is that I told you that sometimes on MCAT exams or DAT exams or PCAT or an ACS final, they would show you a carbon spectrum, right? So this is a carbon right here, and sometimes they would write down letters by it, like Q, T, right? You see these here? So when you see Q, that means quartet, and it's kind of like applying the N+1 rule for the number of protons that are attached to that carbon. So what they're saying is that when you have a Q here, this means that this is a methyl. When you see a triplet, that means that it's a methylene. When you have a triplet here, that's another methylene. We have another methyl group here. And then if it's a singlet, that means it's a carbon that has no hydrogens attached to it. Okay? So that's what that means. Again, usually we don't do that in our textbook, and I don't know why he doesn't, because most standardized tests are obsessed with putting these kind of examples in here. But anyhow, there we go. So we know we have 2 methyl groups, 2 methylenes, and a carbon that has no hydrogens attached. And if you look at the possible answers, look, you got 2 methyls, 2 methylenes, and a carbon. Okay, so this one works. Go to the next one. You get 2 methyls, 2 methylenes, and a carbon. There you go. So that one works. You look at C and D, they all have the same oh, hold on. Here we have 2 methyls. Here we have, but these 2 methyls in this red circle here, those are chemically equivalent. So this is still a possibility. So yeah, we can't use that to figure it out. All right, so what we're going to have to use here is the proton. Now that we've got the carbon. Oh, I just noticed something though. So could anybody tell me what kind of carbon would produce this singlet up here? Sorry, I got a bunch of thoughts in my mind here all at the same time. Can anybody tell me what kind of carbon? If I have a signal that's up at 200 parts per million, this is probably around 210 or something, right? Could anybody tell me what kind of carbon would produce a signal? Yeah, it's a carbonyl. So let's spruce that up, eh? Let's turn that into a carbonyl, and now at least we can eliminate this one because there's no carbonyl. There we go. So now we're narrowed down to 3. And let's take a look here. We've got a triplet that integrates for 3 protons. We've got, what is this? A 1, 2, 3, 4, 5, 6. It looks like a sextet to me that integrates for 2 protons. We've got a singlet over here that integrates for 3 protons. And then we have a triplet that integrates for 2 protons. Okay, well, I'm just going to kind of skip ahead here a little bit because I've looked at this problem already. And you can see that you end up with, if we call this A, we call this B, we call this signal C, and we call this signal D, you can see that they all have an A signal, don't they, right? This would give you a triplet. Or sorry, this would give you a C signal, right? A singlet that integrates for 3 protons. This would, and this would. And so what we're going to have to do is use chemical shifts in order to determine which one is the correct compound. So let's start with A, okay? If we look at A, what's the chemical shift of this methyl group going to be? We have a methyl which has a baseline of 0.9, okay? 0.9 parts per million. But then we have to add what to it? We add 3 to it because it's attached to the oxygen of an ester, and that would give you 3.9 parts per million right? For your signal, that would be C. But you see that it comes out at around 2.1 parts per million. And so this cannot be A. If we go to B, we have this methyl group which has a baseline of 0.9 parts per million. But since it's alpha 2 a carbonyl, we add 1 part per million to it, and that gives us around 1.9 parts per million. And that looks a lot more reasonable, right? This is just, I mean, this is 1.9 right here. I mean, that's close enough to it that it seems reasonable, right? It doesn't seem unreasonable. Let's look at the other methyl group, right, which is going to be this one here. Well, this one is going to have a baseline of 0.9, and it's not alpha or beta to the carbonyl, so that's 0.9 parts per million. And that is right at 0.9 parts per million. If we go to this methylene here, this methylene is going to be a triplet because it's only split by those 2 protons. So that would be these 2 protons here, which have a baseline of 1.2, but they're alpha to a carbonyl. So we add 1 and we get 2.2 parts per million. Well, looky, this is right at 2.1, 2.2. It's pretty close to 2.2 parts per million. And the very last one, you'll have to forgive me because I'm kind of running out of space here. But this methylene, those 2 protons are split by 1, 2, 3, 4, 5. So that would give you the sextet. The methylene has a baseline of 1.2, but they're beta to the carbonyl, right? This is the alpha position. This is the beta position. So you add 1/5 of 1, which is 0.2, and you end up with 1.4 parts per million, which is very close to our sextet here. So B is going to be the best answer, right? Definitely the best possible answer, and B is the correct answer. Right, if you were to try to do the same thing for this one over here, I mean, if you just picked one of the signals, for example, if you picked this methylene here, which would give you the triplet that integrates for 2 protons, right? This one here, what would the chemical shift be? It would be 1.2 plus 3 because it's attached to the oxygen of an ester, which gives you 4.2. So the chemical shift is way too low, and you can see that it can't be this compound. So we eliminated A, C, and D, and we see that the chemical shifts for the proton are pretty consistent with B, and it's also consistent with the carbon shifts as well. And so the answer is going to be the ketone. A little bit more work on this one for sure, but definitely a manageable question. All right, let's skip ahead and take a look at some synthesis, something that's really fresh in our mind. Synthesis problems. Which one did I want to look at? It was question number 3. Okay. All right, question number 3. This is a question I would expect my students to nail. Okay, it says, what is the major product of this reaction sequence? Right, we're taking propyne, which is an alkyne, and we're going to treat it with sodium amide and get number 1. Now, what would number 1 be? It's going to be the alkynide, isn't it? It's going to be this alkynide, which is an anion. Then in the second step, we're treating it with methyl bromide, and that's going to give us number 2. So methyl bromide is this compound, which is a really powerful electrophile. So we're going to get a nucleophilic attack, loss of leaving group, and that is going to give us, this would be 2-butene, or sorry, 2-butine rather. I think I need more coffee. And then in the next step, we're treating it with water, sulfuric acid, and mercuric sulfate. So this is nothing more than a Markovnikov addition of water across a triple bond. Now, of course, there's no Markovnikov or anti-Markovnikov to worry about here. It's not even a concern, but that's going to give us what? We're going to look at getting something that looks just like this, okay, which is an enol, and that enol is going to undergo tautomerization, isn't it? It's going to undergo tautomerization to give us a ketone, and the ketone it's going to produce would be A, that ketone. So just, again, a Markovnikov addition of water across a triple bond. Again, in this case, the Markovnikov or anti-Markovnikov doesn't matter because there is no Markovnikov or anti-Markovnikov when you're dealing with a triple bond. All right, let's see. Let's move on to question 24. There's a lot of synthesis problems in the study guide that involve questions from organic chemistry too, so I had to really look hard for questions that only cover things that we looked at. But question 24, I think, is a really good one. It says you have an optically active alcohol with a molecular formula of C5H8O, and it undergoes hydrogenation over platinum. So that's just treating it with, H2 and platinum to give an optically inactive alcohol. Which of these alcohols is consistent with this data? So what does optically active mean? Could anybody tell me what that means? And it's not a trick. It might not be the easiest question to answer over Teams, but you could just type in a quick answer. If it's optically active, that's just a fancy way of saying what? Optically active, what would that mean? It means that it rotates plane polarized light, exactly. And if it rotates plane polarized light, that means that it's chiral, right? So it means it's chiral. So we're looking for a chiral alcohol, okay? If it's got a formula of C5H8O, that means it's got how many units of unsaturation, right? You get C5 times 2 plus 2, so that's 12. 12 minus 8 is 4. 4 divided by 2 is 2. So it's got an HDI that's equal to 2. But you can see you've got an HDI of 2 here, 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 and here. So they all have the same molecular formula. So you can't solve it using that. Could anybody tell me if any of these alcohols are optically inactive? Are there any that we could get rid of immediately because they're just not chiral? Exactly. Yep. I agree with you totally. You're all 100% correct. I'm trying to thumbs up my students here, which isn't that easy to do on my MacBook. But yeah, you can cross both of these off. Why? Because they are achiral. Excellent work. Right? There's a plane of symmetry down both of them. There you go. We're going to scratch both of those out. Whereas A and B, they're both alcohols. They both have a chiral center in them, don't they? Right? This is a chiral center here, and this is a chiral center here. But could anybody tell me which one of these, if it underwent hydrogenation, you would end up with something that is achiral? Right? If you were to reduce this one, you would end up with this compound. And if you were to reduce the next one, you would end up with this compound. Well, only one of those is optically inactive. Right, the answer is A, because this is a chiral compound, but this is optically inactive, right? This compound in B is chiral, but so is this. So therefore the answer would be A. Give me a thumbs up if you think you could get that one. If you're like, give me a few minutes. I need to look at it, Mr. Dion. Give me a second here. I need my scratch paper, but give me a thumbs up if you follow me on that one. If you're like, yeah, I get it. Cool. What I'm impressed with is how quick you guys are able to answer questions about chirality and determine, which compounds are achiral very quickly. So that's very, very good. Let's try one more question. This one's kind of a long one. It's, this one I would definitely need to bust out the scratch paper for. But it says, which of these two reaction sequences will affect this transformation? Okay. And you see you got a whole bunch of different options here. H2 deactivated palladium, so on and so forth. So what I'm going to do is give me 1 second here. I just want to try something here quickly. Okay, I see that some students have some ideas. What I want to do is this.